Quantum computing draws on the fundamental laws of nature to carry out calculations using quantum bits. So in the same way that classical computers use bits, zeros and ones, quantum computers use qubits that are in a complex state of 0 and 1 that allows them to perform calculations in a different way compared to classical computers.
So if we bring that down to a level I can understand, imagine if we have a big puzzle with many alternative ways out. A conventional computer would have to assess each of those in turn in order to figure out the exit, whereas a quantum computer can look at the whole puzzle and come out with the most probabilistic result.
Yeah, effectively it's a way of computing that will complement classical computers to be able to solve problems that we can't solve today.
So let's talk about what we mean by complex problems.
We're talking about problems with lots of variables that are interacting in complex ways.
So if we think about the way that shipping can be optimized across the planet, taking into consideration all of the different variables like wind and weather and things that you can't predict, quantum computing would be able to help us solve some of those navigational challenges.
Exactly. And another example is modeling the behavior of individual atoms within a molecule,
which allows us to research the development of new materials, and a good example of how quantum is likely to impact multiple industries, not just telecoms.
IBM has an ambitious roadmap that is pushing the boundaries of speed, scale and quality. We're basing this on 3 key pillars: building the hardware, cutting-edge quantum software, and the third is around the network of quantum-ready organizations and communities that we bring together to realize the benefits of quantum computing.
That's brilliant. So we're going to get more qubits, better software to access them, and a whole bunch of people trying to figure out how best to use them.
Exactly. We have over 20 systems available on the cloud today and over 500,000 users. So how do you see these capabilities applying to telecommunications?
Well, we see 2 main areas at the moment, one around machine learning, one around optimization. So in machine learning, we're looking to use quantum computers to detect different types of patterns in data, which can help us solve all sorts of the different problems. Challenges such as where to best place our cell site antennas to get the best possible experience for customers, or how we plan to mix together the different technologies we use to provide fixed line connectivity. These are inherently complex problems, and we're hoping that quantum might allow us to optimize for better outcomes for customers in the future. This is why late last year we chose to partner with IBM so that we could understand how some of these embryonic problems from within the telecom system could be addressed using quantum computers in the future.
And recently IBM published research in Nature, and for the first time a quantum computer has demonstrated that it can produce accurate results at a scale of 100 plus qubits beyond the reach of classical computers today.
And that's a very exciting development for telecommunications, because whilst we haven't quite figured out what problem it can solve, the fact that we can use today's generation of machines to solve real problems at scale is extremely significant for us, and we're determined to find the best way of taking advantage from it.
Absolutely, and this is something that in IBM we're very, very excited about.